paper easier than others, and why the
This
grade,
call is now being recorded.
why the
This
grade
call is now
boundaries
taking notes.
tend to be higher is because they're giving you all the equations for the next few years. So anyone that's in year 9, year 10, year 11, they should be giving you the equations for the upcoming years. So I guess the only thing you need to memorize is the units for each of these. So let's say, for example, if you were given mass, you should know that mass in physics is always measured in kg. If you're given something like energy, you should know that's always in joules. So especially the higher paper as well, they will not give you them in them units. They'll always make you convert them. Another one is time. Time in physics is always in seconds. What else have we got? We've got length. Length is always in meters. We've got speed. Speed is in meters per second. Energy can also be referred to as work, but we'll come to that. In terms of waves and such, frequency is measured in hertz. We've got power, which is measured in watts. It's quite common for them to give that in kilowatts, and then you have to convert that. We've got temperature, which is in degrees Celsius for GCSE. We've got current, which is measured in amps. We've got potential difference, which sometimes they refer to as voltage, but refer to it in GCSE as potential difference, which is in volts. We've got charge, which is in coulombs. And then finally, we've got resistance, which is in ohms. There's others as well. We've got, for example, forces in newtons. Put that here as well. So you have to memorize all these units, and we'll not give you any of the units within the exam. Another thing as well, in terms of content, you can figure out content from the equation sheet that they give you in the exam as well. So this is the one from 2022. It's similar to the one that you will get in your exams this year whenever you sit your exams as well. So as you can see here, the first 1, 2, 3, 4. So these 4 equations here, we've got energy, and there's 4 types of energy that we've got there. So we've got kinetic energy, just going to write it down here. We've got kinetic energy, which the equation it says there is half mv squared, where m is the mass and v is the velocity. So if you were to think about kinetic energy involves movement. So you can figure out from looking at the equation, if you change certain variables in that equation, what's going to happen to the equation. So for example, if I increase mass, so somebody that's heavier compared to somebody that's lighter, they'll have more kinetic energy because there's much more of them to move. Or for example, if something's going a lot faster, so the velocity is a lot higher, then their kinetic energy will also be a lot bigger as well. So we could see them just from the equation, so you don't have to memorize certain factors that affect certain things because they've given it to you in the exam. Let's have a look at elastic potential energy. So the second one here, they've said elastic potential energy, just call it EPE, is half KE squared. Half KE squared, and it's quite good because they tell you what each letter stands for. So K is spring constant and E is extension. So what this basically means is something that's got elastic potential energy. I would say think of a spring, because it's got that elastic potential energy. You could pull it and then let go. So the amount you pull it by, so let's say it starts off there and then I stretch it to here. This is known as the extension. So how could you measure the extension? Well, the length of it has changed. So extension is measured in meters, which is standard for length, which we already know. And then spring constant, essentially, well, spring constant would be different depending on what spring it is. So for example, it could also even be an elastic band. So depending on what you're looking at for elastic potential energy, each elastic model will have a different spring constant. Okay, so again, we can look at the factors. If I increase the extension, so the more I stretch it, then the more elastic potential energy it's got, which makes sense. If you stretch something a little bit and let go, compared to stretching something quite a lot and then letting go, the one that you've stretched by quite a lot would have more elastic potential energy, and it would smack a lot harder when you let go. Now, there's a limit to how much you can extend it, and we call that the limit of proportionality, elasticity, which essentially means if you pull the spring way too much, you could get rid of that. You could pass the maximum amount of extension and it won't go back to its original shape. So if it doesn't go back to its original shape, you've lost the elastic potential energy. Okay, so again, did you start from looking at the equation? Let's have a look at gravitational potential energy. I'll call it GPE. So gravitational potential energy, which is mass times gravitational field strength times height. Mass times gravitational field strength times height. Okay, so let's understand this equation. So gravitational potential energy, well, gravity keeps us down on the ground. There's gravity acting. Now, mass, so in kg, of course, the greater the mass there is, the more gravitational potential energy you need to keep that down. So something as little as a bottle, which has less mass than yourself, needs less gravitational potential energy to be able to keep it down. Okay, the gravitational field strength, well, this will change depending on where you are. So for example, on the Earth, it's 9.8. Sometimes they refer to it as 10. But the moon, the gravitational field strength is a lot less. So we could say 1.1. They tend to give you these values in the exam though. So of course, if you're somewhere like Earth compared to the moon, you're going to be flat down because it's a higher number. Okay, and then in terms of height, so how can you measure height? Well, height's just in meters. So let's say, for example, a person, and they're dropping a ball from here compared to somebody that's dropping a ball from like right on the top. Let's just say they're dropping it from there. So because this one has a greater height in the second example, there's going to be more gravitational potential energy needed to keep it, put it all the way down. So you can see if you increase this number here, you also increase gravitational potential energy. So there's no need to actually remember what factors affect each energies. It's all in the equation, just like I said. And then finally, we've got change in thermal energy. So it's represented by delta E. This delta just means change in. So anytime you see that triangle, it's a change. Okay, so the change in thermal energy is mass times specific heat capacity times, I think, change in temperature. Yep, so delta theta. Okay, so change in temperature, to work this out, because it's change, we've got that triangle, you do the final temperature minus the initial temperature, so the starting temperature. That's how you find the change in temperature. They usually give you two of them in the question that you're given. Specific heat capacity, again, they will give you this, or sometimes you can work it out. Now, what specific heat capacity is the specific heat capacity of a substance is the amount of energy required to raise the temperature of 1 kg of substance by 1 degree Celsius. Now, without fail, I have seen specific heat capacity come up every single year in a paper, and you could just figure out how to work it out by looking at this equation here, so without memorizing it. So specific heat capacity, let's understand this definition. So of a substance is the amount of energy required to raise the temperature of 1 kilogram of substance by 1 degree Celsius. So why the whole 1 kg by 1 degree Celsius? Well, this is just to keep it uniform. So let's say, for example, I want to work out the specific heat capacity of aluminium and of water. Well, if I have a lot of water, so more than 1 kg worth, I don't know, let's just say, well, instead of using aluminium, let's do oil, actually. So we've got two liquids that we're comparing. Now, if I'm comparing how much energy it takes to heat this, if I had less oil versus a lot of water, of course, this will be a lot easier to heat because there's less of it. Whereas the water would be harder to heat because there's more of it. So the reason why we say 1 kg of substance is so you've got a fair measurement of each of them. And again, 1 degree Celsius, because then they've got the same amount of change, essentially. So you compare that. So specific heat capacity values, we already know them. So I can give you some as an example just to show you and what they look like. They usually give you this table in the exam. Okay, let's have a look. Specific heat capacity, I want the values. Yeah, so for example, we've got some here. Let's copy these over. Okay, so here's some examples. So we can see the specific heat capacity of something like iron 0.412 is a lot less than water because it's a lot easier to heat iron because it's a metal, and so on. So yeah, they give you these values. Now, it's quite a common question for them to ask, how can you measure the specific heat capacity of a substance? So the way I remember it is I would not recommend memorizing like the whole method, but you can kind of figure it out just again by looking at the equation. So if I rearrange this equation and I make C the subject, because that's the specific heat capacity. So let's rearrange it. If I want C by itself, I need to get rid of this M and this delta theta, which is the change in temperature. So since we're timesing by both of them, the opposite of timesing is dividing. So I've just got the change in thermal energy, delta E, divided by the mass times the temperature change. So that's how you work out specific heat capacity of a substance. How can I work out each of these? Well, mass, you can just figure this out actually. Mass here, we can essentially measure it using a scale, right? So that's kilograms. So think of a way that you can measure the mass of something. We've then got change in temperature. Of course, you could use a thermometer for the change of temperature, right? So measure the starting temperature, measure the end temperature. And then finally, the change in energy, well, which you'll see how we can relate power and energy to each other. So there's means of actually finding the change in thermal energy as well. Okay, so let's go back to the top here, look at the equations. Okay, so then you've got two other equations. So I'd highly recommend getting this sheet printed out. You could just Google it for your exam board. So have a look at what it looked like the year before, and most likely that's what you'll get this year. But as you can see for power, which is measured in watts, we've got two equations, energy transferred over time and work done over time. Now, both energy transferred and work done. Okay, hopefully you can hear me now. So as I was saying, energy transferred and work done, both measured in joules, because essentially they're the same thing. It's just different wording that they could potentially use in the question, which is why they give you two different equations for them. Okay, so they might ask you, well, what exactly is the definition of power? Now, you know power is measured in watts. But if you look at the equation for power, it's the energy transferred. Again, you're given these in the exam, over time. And we know energy transferred is measured in joules, and we know time is measured in seconds. So if I want to define power in terms of energy transferred and time, I could just say power. So you could say one like power unit essentially, rather than saying 1 watt, you could say it's 1 joules per second transferred. So essentially 1 watt means that every joule that's transferred in a second, and I can just get that from the equation because I'm dividing by it. Okay, so yeah, that's the definition of it. Rather than memorizing it again, just get it from the equation. Now this equation is a little bit different. The equations that we were looking at beforehand, they're just quite straightforward, where it's just something equals all of them times by each other. So if I increase any of these values, you know that it's going to increase the thermal energy. So if I increase temperature change, you're increasing the energy change. If I increase the mass, I'm increasing the energy change. If I increase specific heat capacity, I'm increasing the energy change as well. But if we look at this one here, we've got something dividing by each other. So if I increased the energy transferred, so something like a TV would require a lot more power and energy transfer compared to a phone, for example. So therefore it needs more power, so a higher wattage. So if I increase this, then, so if I increase energy transfer, then of course I'm increasing the power. Now what happens if I increase time? Well, it's the opposite. If you make the denominator bigger of something, you're decreasing the overall power. Now I'll just explain this to you. I'd recommend putting in a few numbers just so you can see what happens when dividing. So I'm going to keep the energy transferred the same. And I'm going to increase the number on the denominator just to show you what happens. So let's say 1/2. So a half. As a decimal, a half is 0.5. Let's increase the denominator to 4. 1/4 is 0.25. So you can see as I increase the denominator from 2 to 4, the overall number has decreased. It's gone down. So just like I said over here, if I increase time, so the denominator, the actual power will decrease. Is the opposite. You also need to know this for bounds and error intervals for maths as well. This concept, which confuses quite a lot of people. I'll increase the number even more just to prove it to you. Let's put 10 over. 1/10 as a decimal is 0.1, and you can see 0.1 is a lot smaller than 0.25. So the number's getting smaller. Overall number is getting smaller as the denominator is getting bigger. Is getting bigger. So a lot of people get confused with that concept. So I'd recommend just plugging in some numbers and see what happens. So I've just proved it there, essentially. Okay, what else can we look at? Let's okay. So yesterday for the chemistry class, we spoke about conservation of mass. Now, a really important law for physics is conservation of energy, which essentially means energy cannot be created or destroyed, just transferred. So say, for example, I think what example I can use. Let's say a Hoover, example. Now, the whole purpose of a Hoover is essentially to clean mess, right? So the electrical energy that you put inside the Hoover, electrical energy, changes to mechanical energy, which is mechanical just means movement, which is mechanical energy of the rotor spinning in order to pick up the mess from the ground. Now, at the same time, you've also got sound energy, which gets emitted, which we don't want a noisy Hoover. It's not really useful. So we call this wasted energy. Another wasted energy that could come from the Hoover, when you're hoovering, the Hoover can get quite hot. So thermal energy. Again, in this case scenario, we don't care about thermal energy from a Hoover. So again, this would also be wasted energy. Thinking about the purpose of the Hoover. We could think of something else as well. Let's say a heater. Now, the heater I'm thinking in mind is those fan heaters. I'll just show you a picture so you know what I'm referring to. You might have this in your house. You might not. Let's see. So these ones here where the light comes out as well. Okay, copy image, just so you've got something to compare it to. So it's quite common as well to analyze electrical appliances in the exam, and they'll say what energy has been transferred, what's the wasted energy, how efficient is it, and such as well. So in this case, the heater is working by, again, electrical energy. You have to connect the heater to a power supply in order to be able to essentially for it to emit heat. Now, the useful energy from this, the whole point of the heater is to warm you up. So thermal energy in this case is the useful energy. I'm going to highlight the useful energy in each of these. So this is useful. This is useful. Okay, but what's all the wasted energy that's coming out of this heater? Well, there's light energy which is coming out. So you don't necessarily need to see like why is it as orange as it is. So again, that's wasted. It defeats the purpose here. Sometimes these are quite noisy as well. So again, sound energy could come from them, which we don't need. So again, that's wasted energy. Now, all this energy has to come from somewhere. So the electrical energy that's going into this heater is getting used for these two and it has no use. So it's like you're paying more to put the fan heater on, but for energy that you're not using, it's just getting wasted. So these ones are quite expensive to run in a household compared to something like oil heaters. I'll just show you what an oil heater is. Oil heater. So these ones here. Now, the reason why these ones are a lot more energy efficient is because there's no light coming from them and there's no sound coming from them. So all that electrical energy that you're putting into that heater is just being transferred to thermal energy. So therefore, it's a lot more efficient, a lot cheaper to run in the household as well compared to the fan heaters. Okay, so that's a little bit about power efficiency and knowing about other energies as well. Now, sometimes they might use the word dissipated. So dissipated energy is essentially wasted energy that's gone. So for example, in the case of the Hoover, this thermal energy that's getting emitted, it's getting emitted and it's just dissipated. It's gone into the surroundings and it's wasted. So by thinking of this conservation of energy, energy that's always been around the Earth millions of years ago is the same energy that's here today. We've not created or destroyed energy. We just keep transferring it. An analogy that I like to use as well. So for example, water that's been on the earth as well for millions of years is the same water that we're drinking today. The water that you could be drinking right now had a different place millions of years ago, maybe on the other side of the world, for example. So again, we can't create or destroy that as well. It's just constantly transferred through the water cycle. Okay, let's move on. Okay, so what if I wanted to reduce unwanted energy transfers? So what you could do is, so reducing unwanted energy transfers. So one thing you could do is use lubrication. Now, what this essentially means is like putting, let's say, oil between two objects. And the reason why you would do this is to reduce friction between two substances. So that's one way you could use. So you could use oil to do that. And then another method is thermal insulation. Now, this is most likely used in houses. So say, for example, you want to keep your house as warm as possible without the need of heaters, for example. You could just reduce the amount of heat that's essentially leaving that room. Now, another misconception as well is, let's say it's cold outside, somebody opens the door and they say, close the door, the cold is coming in. There's no such thing as cold being transferred, it's the heat that's escaping that room. So stuff you could do to prevent this, you could have double glazed windows compared to single glazed, which essentially a double glazed window, you have a window, you've got an air gap in the middle, and then you've got another window. So when the heat essentially leaves, it won't just leave straight out. There's an air gap there which will stop it from essentially leaving. You could have the cavities that get pumped inside the wall, so it's a bit like glue kind of inside the walls to again reduce that unwanted thermal transfer of energy. You can put so you can put drafts like under the door to kind of eliminate the amount of gaps and so on. Okay, so there's two other words that you also need to know about, conduction and convection. And again, these are methods of heat transfer, but in different matters. So conduction is the transfer of heat in solids, whereas Convection is a transfer of heat in fluids. Now, when we say fluids in physics, we always mean liquids and gases, not just liquids. That's another common misconception as well. So fluids refers to both liquids and gases. Okay, that's conduction and convection. And then another thing we've been speaking about throughout all of this as well is efficiency. So you might have to work out the percentage efficiency of an appliance. And you should see these efficiency stickers when you buy electrical appliances because it's a legal requirement here. So they could give you one of these in the exam to annotate. So efficiency stickers might come up like that. Yes, these ones here you might have seen in electrical appliances. So of course, let's copy this so you can see. The better the score on there, the less unwanted energy transfers there are. There's the ones that we want. So let's get them here. But then in turn, it means that it'll be more expensive. So you can see it's got an A grade, which is a good grade compared to something that's a G, for example. But the appliances that'll have a lower energy rating will be cheaper to buy, whereas the ones that have a better energy rating are more expensive to buy because they do their job better. So it's that balance that you need to get. So you should notice these labels whenever you're buying electrical appliances and have a look. Okay, so energy resources, where can we get energy from? So there's renewable energy and there's non-renewable energy. So renewable energy, which essentially means there's infinite amount of it, we won't run out. And then there's non-renewable energy. So which is essentially a finite amount. So once we finish it, then it's gone. So renewable energy is one that can be replenished as it's used. So some examples is solar, which is from the sun. We've got wind, so the turbines that you see when you're driving on the motorway, that's how they get the wind. We've got water waves, so essentially dams that are created in order to generate energy, essentially electricity. We've got biofuels, tides, geothermal, hydroelectricity, and so on. And then in terms of non-renewables, it's essentially ones that can't be replaced, so stuff like fossil fuels. We spoke again a little bit about this in chemistry yesterday, so in terms of crude oil. We've got stuff like coal. So coal, once they find it and you use it, that's it, it's gone. We've got oil, natural gas, and so on as well. Okay, so I'm sure you could guess the advantages and disadvantages of each. Is kind of similar to what we spoke about yesterday in chemistry as well. So these would emit gases contribute to global warming. Now, what you need to think about with these as well is you don't just get the energy, you also have to transport that energy and store that energy as well. So you need to take them costs into account as well. So for example, fossil fuels, crude oil is not in the UK, for example, we would get that from another country, say the Middle East or Russia and so on. We get it from that side. So it costs energy to transport it here for us to have that energy in terms of electricity. So you have to take all that cost also into account as well. Okay. So what's the reason why we don't just use renewable energy and not non-renewable energy? It's because of demand. So because demand is quite high, renewable energy resources is not going to be enough to meet that demand compared to something like fossil fuels and oil. But then the issue is once these finish, then what? So that's the balance of argument in it. Okay, moving on. Let's have a look at these equations on top here. Okay, let's have a look at this one here. So density equals mass divided by volume. That's quite a common one that you also need to know within physics as well. So density. You don't need to remember the definition because again, they've given you the equation. It equals mass divided by volume. So let's use the same ideas we've been using before as well. if I increase the mass, then of course the density will increase. So if I increase the numerator value, then the density will also increase. So something that's got more mass inside it, the more dense it is. The way I think about it is, imagine you've got water, for example. So water's your volume. If you've got water and you've got some sugar in it, for example, or salt, and then I put in that same water more mass of it, so a lot more, you can see this is going to be more dense because there's a higher amount of mass inside it. So it makes sense as well. But again, you can figure that out from the equation. Now with volume, if I increase the volume, because it's in the denominator, that's going to decrease the density. And again, if you think about it logically as well, if I've got a glass of water, I say this much, and it's got that much mass inside it, let's just say of salt again. Now, if I double the amount of water that's in there, keep the same number of mass, now this is less dense as expected. So I've increased the volume, but now the density has decreased because there's less mass in more amount of water. So yeah, you can figure that all out from the equation as well. And in terms of units as well, it's quite common for them to ask you what's the units of so-and-so. Mass tends to be in kilograms, volumes. They could potentially give you in anything really. So be careful of what they give you volume in, because then that'll affect your density units. So let's say mass is in kilograms and volume is in centimeters cubed. In that case, your density unit will be kilograms over centimeters cubed, because you're dividing, right? So that's just a divide sign. That's here, as you can see. We just show it as a slash. So that's how you figure out units as well. Okay, moving on. Okay, let's talk about some key conversions as well. We've spoken quite a lot about units, so there is a very heavy emphasis on units within physics as well. Especially for the higher paper, you will most likely be changing the units of equations. So you should know 60 seconds is in 1 minute. So therefore, to go this way, we divide by, sorry, hold on. To go this way, we're dividing by 60. This way, we're timesing by 60. Make sure you also know the 60 minutes in 1 hour. You know all these for maths as well. And then when they're talking about a day, that's 24 hours that they're speaking about. Okay, so other ones. Anytime you see the word kilo, the word kilo refers to 1,000. So let's say in 1 kilogram, I'm going to have 1,000 grams. So kilo refers to 1,000. If you see the word mega, that refers to 1,000,000. So 6 zeros. And if you see the word giga, that refers to 1,000,000,000. So 9 zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9. To be aware of these words as well. Kilo tends to be the most common ones, but they can sneak in mega and giga into there as well. Okay, what else? If I'm going from centimeters to meter, I am dividing by 100, because there's 100 centimeters in 1 meter. If I'm going from grams to kilogram, we divide by 1,000, as we've already spoken about there. Kilo means 1,000. This is a weird one that students forget. If I'm going from centimeters cubed to meters cubed, I'm dividing by 1 million, and I'll explain why. So centimeters cubed is essentially centimeters times centimeters times centimeter. So this here, I'll just prove it to you. It's 1 centimeter times 1 centimeter times 1 centimeter. Whereas with meters, it's 1 meter times 1 meter times 1 meter, because it's meters cubed. So if I times meter 3 times, I get that. But if I want to change these meters to centimeters, I know each of these are 100, so that's 100 centimeters, timesing by 100 centimeters, timesing by another 100 centimeters. And if I do 100 times 100 times 100, that's where your 1 million comes from. So 1, 2, 3, 4, 5, 6 zeros. So that's where it comes from. That trips up a lot of students as well. It comes up in maths as well as physics. And let me just get the next thing up. Right, let's have a look at forces now. So a force is measured in newtons. Now, when looking at units, any time a unit has a capital letter, so for example, Newton has a capital N, it's because it's been named after somebody. So same with the joule, for example, joule is also with a capital J because it's named after the person surname. Whereas something like, where's the unit? Something like time, which is in seconds, is a small s, not a capital S, because it's not named after a person. It's just, that's just what it is. So yeah, if it's named after a person, it tends to be capitals. If not, it just tends to be lowercase. So that's just why sometimes you'll see capital units and sometimes you'll see normal units. Okay, so it's measured in newtons because it's discovered by Isaac Newton. Now there's three, before speaking about forces, actually, we need to talk about the difference between scalar and vector quantities. So scalar and vector quantities. Now, the definition of scalar is something that has size. So if I say you are 6'3", that's a scalar. I've given you a number with it. So that size we're going to refer to in physics as magnitude. So magnitude just means the size. So scalar has just a magnitude, whereas a vector quantity has size, so magnitude, plus direction. Okay, and in physics, we tend to use vector quantities a lot more than scalar quantities. So let's give a common example. Speed is a scalar quantity, whereas velocity is a vector quantity. So technically they're the same thing, but one just has direction as well. So just to give an example, I could say the speed of a car is 10 meters per second. I could then specify the velocity of it, which is 10 meters per second north. So I've given direction to it, essentially. So that's the difference. Most likely you will be using vectors within physics over scalars because direction's important with a lot of these things. Okay, so what's some other examples? Well, distance is a scalar quantity. The vector version of distance is called displacement. It's probably worth as well writing what these are measured in. So speed is in meters per second, velocity meters per second, distance in meters, displacement in meters. So just to give you an example of distance and displacement, because people can't really figure out how can I put a direction on that. Let's say you're at your house, so that's home, and you go to the shop. So this is the shop. So if you go walking to the shop, let's say the shop is 10 meters away, and then you also come back from the shop home. So you come home as well. So that's another 10 meters. So you've walked from home to the shop, 10 meters. You've then come from the shop home, that's another 10 meters. The distance that you've traveled is 10 meters plus 10 meters because that's how much you've done altogether, so 20 meters. However, the displacement, because it's a vector quantity, is going to take the direction into account. So going from your home to the shop, that's going to be the positive distance. So you've gone 10 meters from your house to the shop. You then come back from the shop home. Now, because it's in the opposite direction, now that's a negative 10. So 10 meters minus 10 meters, your displacement is 0. So overall, you've not moved any distance because you've ended up at the same starting position. So that's the difference between distance and displacement. You can see the answers are completely different. Okay, some other examples of each of these. Just highlight this. So that's the definition. Okay, stuff like mass is scalar, so which is in kilograms. We've got temperature, which is scalar. We don't add a direction temperature. And time. Time just goes in one direction, just forward, so we don't class it as a vector, and that's in seconds. So temperature degrees Celsius times seconds. Okay, so that's a few of the examples of scalar quantities. Let me just write quantities on top of here. Okay, so what about vector quantities? Well, forces are vector quantities. And the reason why forces are vectors is because you're always specifying the direction with forces. So when we draw the free body diagrams, let's say, for example, this is a human person. The force acting down on them is their weight. Maybe, or let's just say it's a car actually. So a force acting downwards on the car is weight. You could say there's a forward driving force as well onto that car. Going backwards as well, there's like air resistance on that car as well. So you can see direction we specify with forces. So forces is a vector quantity, which is measured in newtons. We've got stuff like acceleration, which is measured in meters per second squared. So we'll come on to that, why it's measured in that unit, but you do need to know that. We've got stuff like momentum. Momentum is the study of motion in physics, which we'll come on to as well. And yeah, that's a few examples. So acceleration, I just want to touch upon this. Let's go back to the top with the sheet that's up here. Okay, here, acceleration. So acceleration is delta V, so change in velocity. So final velocity minus the initial velocity divided by time. So let's say you forgot the units for whatever reason. How can you figure out the units for acceleration being meters per second squared? Well, let's do it down. So acceleration is change in velocity, so delta V over time. Now we know change velocity, so change in velocity is final velocity minus the initial velocity and then divided by time. So we know the top unit of velocity is measured in meters per second. So meters per second. And we're dividing by time, which is also in seconds. Okay, so let's do a little bit of maths on this. We're going to use our fraction rules here. And even though if you memorize acceleration in meters per second squared, you might be given a scenario where you need to figure out the units or something without being able to memorize it. So this is what you do. So just to explain again, on the numerator, the velocity unit is meters per second. On the denominator, we've got seconds. Now, I've got a fraction and a fraction. That meters per second, I can write it like this because this is a divide symbol. And then I'm dividing by seconds. So I'll just throw that out. Okay. So I've got meters per second divided by second. I can put that over 1. Now, remember, when you're dividing fractions, you do keep, change, flip. So keep the first one, change the divide to a times, and then flip the second one over. So 1 over s. If I times this across, m times 1 is just m. S times s is s squared. Now this divide sign, I could just do it as a slash, and I get meters per second squared. So as you can see, I've just proved it to you. So you can use your fraction rules within this as well. So be quite comfortable in doing that as well. Okay, another thing I want to mention as well. So with the distance, speed, and time equation, all of you will be used to using this. Distance, speed, times. So it's in alphabetical order. I would still recommend keep using that, but just be aware it's written differently on your equation sheet. It might not be for certain exam boards, but usually it's written completely different. So I'll show you that equation that's on the equation sheet here. So here you go. Distance traveled equals speed times time. So that's okay. That's what we've just said, the triangle, right? So distance traveled equals speed times time. However, if you look at the letters are S equals VT. So their triangle would look like this: S, V, and T. So if you look, T is the same, but S represents distance in physics. For whatever reason, it doesn't make sense. So that S represents distance, not speed. So don't get confused by that. So which is there. And the V represents velocity or speed in this case. It says speed, but they should use the word V. So they're the same. So if you ever get confused, don't use the one that they give you on the equation sheet. You could just stick with what you've used there. But the reason why I'm saying is I've seen a lot of people assume that S is speed and they think speed equals VT, but it's not. S here represents distance. We can see it here as well in this equation. We've got W equals Fs, the work done, equals force times S. Again, people assume is speed. It's not. It is the distance, which is measured in meters. So just be careful of seeing that S on here as well. It comes here as well. There's the S, which represents distance. So just a bit bizarre because you are used to using D for distance. Okay, let's have a look if there's anything else there that's worth mentioning. Okay, what I'm going to do now is just before starting a new topic, so I'm going to go over the forces and just speak a little bit about forces. I'll give you a 5 minutes break now and then we can just continue straight after that. So if you come back for 1:55, I'll just put it in chat as well. So for 1:55, and we'll continue from there. Okay, I'll see you in 5 minutes. Okay, let's continue. So starting with forces, we'll start off with Newton's three laws of motion. So the first law, you need to remember each of these. So we've got the first law, we've got the second law, and the third law. So I would say the easiest law to remember out of the three is the second law. It's just the equation. And again, I'm going to be repetitive. It's on the equation sheet. So force equals ma, where m is the mass and a is the acceleration. Acceleration. So acceleration measured in meters per second squared. We've got mass in kilograms, and then force, of course, is in newtons. So yeah. Okay, so we can see if you increase mass, then of course you're going to increase the amount of force. If you increase the acceleration, then of course you're going to be increasing the force as well. So yeah, the second law is essentially just the equation, which is on the equation sheet, which is, yeah, so here. Force equals mass times acceleration. Now it says resultant force there on the equation sheet. Now what resultant force means is the overall force. So let's explain the definition of resultant force before I go on to the first definition. So what is the resultant force? We'll come back up here. Result and force. The resultant force is essentially the overall force. And it's going to depend on what it is that you're looking at. So let's say, for example, we'll use a car example again. Okay, so we've got a car. Now the forward driving force of this car, let's say it is 50 newtons, and the air resistance that's acting on that car backwards whilst you're driving because there's wind essentially pushing back on it, we could say it is 20 newtons. So therefore the overall force, which basically means the resultant force, is going to be 50 newtons minus 20 newtons because they're in opposite directions. So we're minusing them from each other. So 50 because that's forward, opposite direction will be minus. So like how we said, forces is vector quantity, direction matters. So 50 minus 20, so we've got 30 newtons of resultant force. Just to prove to you that direction does matter, again, let's use a car example. And this time we've got two forces acting on it forward. So we've got 20 newtons and we've got 15 newtons. What's the resultant force in this case? The resultant force would just be 50 plus 20 this time because they're both in the same direction, so 70 newtons. So remember, direction matters in what you're looking at for each of these. So that leads quite nicely to the first law because we're speaking about resultant forces. Now, what the first law says is if the resultant force, if the resultant force of something equals 0, if that object is stationary, and remember stationary means still. So if the object starting stationary, if the resultant force is 0, then it will stay stationary. So it seems like common sense really, right? If you're still and then no force is acting upon you, so 0 newtons, you will just stay still. So that's what the stationary means. However, if your resultant force is 0 newtons, but let's say you're moving in motion essentially, it's going to stay constant, so you're going to stay at the same speed. Okay, so just to reiterate, if you're stationary and your resultant force is 0, you will stay stationary. However, if you're in motion, but your resultant force is 0, then you will stay at that constant speed of motion. You won't change, increase or decrease in speed. So it continues to move at the same velocity. I should really say velocity over speed. Just so direction is taken into account. Okay, so that's what the first law is talking about in terms of resultant force being equal to 0 and what happens. And one other thing I want to mention as well about the this second law here, we've got F equals ma. If I rearrange that and make acceleration the subject, so I'm going to divide by m, so I get F over m, you can say that acceleration is inversely proportional to the mass of the object. So this is relating a little bit to maths. So I'm not sure if you've done direct proportion and inverse proportion yet in maths, but what you can say here is that force is directly proportional to acceleration. And the reason why we can ignore the mass in that case is because mass should stay constant. You're not going to be changing the mass of something that you're measuring the force of. You're going to be changing its acceleration, so how fast or slow it's going. So therefore, you can say force is directly proportional to acceleration. If I rearrange that, I can also then say acceleration is inversely proportional to mass. So a bit of a hard one to get your head around that students struggle with. But it's all to do with rearranging the equations that they're giving you in the exam. So yeah, that's a bit of a higher tier mindset. Okay, what does the third law say? The third law says, this one not a lot of students like. So when two objects interact, for every action, which essentially is a force, right? So when you do some action, let's say I'm pushing a wall, that action I'm doing is a force that's on it, a push force. So when two objects interact with each other, for every action, there is an equal and opposite reaction, which essentially that reaction is also a force. So just to give you an example, let's say I have, I'll do the third law example here. So I just remember this example to understand it more. Let's say we've got a brick wall. I'll draw a bit there. Okay. Okay. We've got a brick wall, and then we've got somebody that comes along and they push the wall. So they're pushing the wall. Now the wall's not going to fall down. They're just pushing the wall, but that wall is giving an equal and opposite reaction force back to the person as well. So that's the reason why nothing is happening. The wall is staying upright and the person's not moving either. So this is an example of the third law. So I'll just write a person pushing a wall in case you can't understand what the image is showing. Okay, so they're the three laws of motion that Newton came up with for classical physics. Now, let's take a step back and look at a certain type of force called weight. So a common misconception is, again, in real life, when you are told to go measure your weight, you're not really measuring your weight, you're measuring your mass. So the equation for weight is mass times gravitational potential energy. Again, let's go back to the top. It should be here. There it is here. So weight equals mass times gravitational field strength. So weight essentially is a type of force. So weight is a type of force, and we know that forces are measured in newtons. So therefore, weight, the unit for weight is newtons. So try and not get confused by that. A lot of students put weight as kilograms, but when you're going to measure your weight, like on a scale, that's not your weight. That's really your mass that you're measuring. So mass is in kilograms, and then gravitational field strength again will be different depending on where you are. So it's measured in newtons per kg, which makes sense if you ever do end up forgetting the gravitational field strength units. If I've got newtons on the left-hand side, and on the right-hand side, I am timesing mass, which is kilograms, times something, which I don't know the gravitational field strength. Well, I want newtons on the left-hand side. So of course I'm going to be timesing by newtons, but I need to cancel out this kilograms. So if I times by kilograms underneath, they cancel out. So that's how you get newtons on each side. So newtons per kilograms. Again, on Earth, it's a 9.8. Sometimes you might see it as 10. So mass is the same wherever you go. So if you're measuring your mass on a different planet or on the moon or whatever, the mass is exactly the same. But it's your weight that changes. So you would weigh less, your weight would be less on the moon because the gravitational field strength is less compared to your weight on Earth. So yeah, you can be asked that in an exam, the differences between weight and mass. You would say weight is a force, mass is constant, mass does not change, and it's measured in kilograms. Okay, and if we're representing weight, weight is always measured downwards because of this gravity that's here. Okay, so what else can we speak about in that? I'll just put some examples of G. So G is 9.8 newtons per kilogram on Earth. I would recommend memorizing that one, but for the moon, I wouldn't memorize that one. Let's say 1.6 newtons per kilogram for the moon. So yeah, they won't expect you to memorize that. You need to be really confident with rearranging these equations as well. So you might be given weight and gravitational field strength, and they'll say work out the mass. So you should be quite confident rearranging that. If I'm making mass the subject, I need to get rid of this G. So since I'm timesing by G, I need to divide by G. So W divided by G. So the same equation, rearranged. So I'd say that's the difficult part of physics, memorizing the units and understanding how to rearrange everything. But you can see all the answers are given to you in terms of what factors affect what in the equation sheet. Okay, these diagrams that we've been drawing, we call these free body diagrams, but instead of drawing the car, you would represent it by a dot. So that's the body essentially. So if you see them like that, and this usually the size of the arrow as well represents that size of force as well. So you can see the 20 newtons one would be a lot shorter than the 50 newtons, for example. Okay, let's move on. We've got contact and non-contact forces. So let's cover these: contact and non-contact forces. Okay, so a contact force is where the objects are actually physically touching. So objects physically touching. Now, for example, I'm sat on a chair right now. So acting down on me is gravity, but also acting upwards on me is a contact force as well, because I'm sat down, the objects are touching each other. Okay, non-contact forces then is where the objects are not physically touching. So objects, I'll say, are physically separated. Okay. So I'll give some examples of each as well. So examples of contact forces can be friction. If you think about friction, if you're rubbing your hands together, the heat that's generating is caused because of friction. There's two objects touching each other together. When you're rubbing your hands, that's friction that's causing it. Friction is also with a car. Again, we can use that example. The tires being on the road, tires going over the road, that's friction. So it allows the car to essentially stick with the road, essentially. So we've got friction. We've got air resistance. Imagine somebody jumping from the sky, parachuting. As soon as they open that parachute, the air is colliding with the parachute. So air particles onto the parachute. So that's air resistance. We've got tension. We've got the normal contact force as well. So just like I was saying, being sat on a chair, for example. Some examples of non-contact forces is gravitational force, because gravity is going to be on this Earth regardless of anything touching anything or not, everything is going to be kept down, and that's a non-contact force. So gravitational force, we've got electrostatic force. Now, remember we spoke about this yesterday with ionic bonding and metallic bonding. Electrostatic force is essentially something that's between a positive and a negative charge. So this comes in magnets as well, which you need to know about for physics as well. What else have we got? We've got magnetic force, as I've just said as well. Okay, let's continue. Let's go on to elasticity. So we spoke a little bit about elastic energy, but you can also think of elastic forces as well and what you can do to a string. So there's a few things that you need to know what you could be able to do to a string. So forces, a spring, sorry, and elasticity. So what you could do is you could, let's say we had a spring, you could pull it on each end. So I could pull it that way and that way. So pulling it across each other. So a force coming up here and a force coming up here. We call this stretching. So we've stretched the spring essentially. So you're pulling it and essentially it gets longer. When you let go, it goes back to each other. Okay, so stretching out the spring. You could also, we've got the spring again. This time you could push the forces going down on it. So we're essentially got a spring and we're squashing it together. Don't use the word squash though, we use the word compress. So compress means pushing it close together. Okay, and then finally, you could also bend it as well. So to show that, let's say we've got a spring, we could get the forces, we could push it that way, I could push it this way as well, and I could also push it that way. So I'm kind of like bending it, essentially. So we're bending here. Okay, so there are three things that you can do with a spring and with elasticity when applying forces to it. Okay. Um, Okay, so what you need to notice with this as well is there's more than one force that's being applied to each of these scenarios. So for example, if I just pull it from one side, I'm not actually pulling the spring, I'm just moving the spring. So there has to be more than one force on each of these scenarios for it to essentially change shape. If you were just doing one force, you're essentially just moving the spring. You're not actually stretching, compressing, or bending it. How do we define an elastic object? Which you can be asked. So an elastic object is defined as something, so materials, that can return to its original shape and size after being stretched, compressed, or bended. Sorry. So after it's being stretched, compressed, or bent. So stuff like the spring that we said above, we can also say a rubber band as well. So a rubber band is another example that exhibits these behaviors. Okay, and then the equation for this is similar to the elastic potential energy where there's a spring constant and extension, but instead of energy this time, it's force equals the spring constant times the extension. So instead of energy is force, and again, you're given this one on the equation sheet. You should do anyway. Yeah, over here. So that's also given there as well. So spring constant, remember spring constant would be different depending on what object it is. And then the extension is how much you pull it. So that's measured in meters and then newtons. And so there's quite a lot of overlap as well with these. Okay, just for the last 15 minutes, I want to speak a little bit about waves. So we've touched upon waves as well. Now, we've either got matter now, so we've got matter, or we've got waves in the world. So what matter is something that's solid, liquid, or gas, which you could see around, so like a solid laptop or phone or whatever you're using, liquid water, gas in the air, so oxygen. This is all matter. Now, waves, there's two versions of waves it can be. We could have transverse waves, or we could have longitudinal waves. And the more common waves that we see are transverse waves. So the way transverse waves look, a bit like a sine graph in maths. So it's just a, let me draw that a bit there actually. Like so. And then longitude, so we can see each peak is essentially similar. Whereas with longitudinal, it can start off squashed and then it can go loose and then it can go squashed again. So it's different. Let me get a better diagram than what I've got and put it on the sheet. Transverse and longitudinal waves. So there you go. That's a good example. Let me speak a little bit about these as well for the last 10 minutes. Okay, transverse waves and longitudinal waves. Now, you need to know some examples of both transverse waves and longitudinal waves. Now, transverse waves are all the waves that are essentially in the electromagnetic spectrum, which we're going to speak about. So the electromagnetic spectrum waves, we've got stuff like light, which is in the electromagnetic spectrum as well, water waves. So think about when you've got a puddle and you throw like a rock inside it and then it forms them ripples in the water. I'll show you how that explains it. Yeah, just like that, for example. So it's essentially a ripple of water. And then we've also got seismic S waves. Now that's just referring to a certain like earthquakes. Anyone that's doing geography might know what seismic waves are. We'll leave that example though. And then for longitudinal waves, the most common example is sound waves. So when they exhibit behaviors like longitudinal waves, and then seismic P waves as well, but we'll keep it just to sound waves. Now, let's speak a little bit about the electromagnetic spectrum in the last 10 minutes, just because of time. The electromagnetic spectrum is the, I'm doing a new page, order of waves in spectrum, essentially. You need to memorize this. You won't be given this in the exam, unfortunately. So it starts off with radio waves. Now, for each of these, you need to know the frequency of them, the wavelength, and so on as well. But because it's in a spectrum, it follows a pattern. So it starts off with radio waves. Radio waves is essentially how the radio works. So when you put the radio on in your car, that signal is essentially coming from a radio station that's come into your car, which is why you can hear the radio. After radio waves, you've got microwaves, which isn't just used for warming food, by the way. Microwaves are also used within data transfer as well. After that, we've got infrared. Now, a common infrared example that I think of is like thermal imaging. So when like police go inside a house and it's dark and they get pictures like this on the camera, I just want to image. So like this is infrared essentially. So the hotter parts will be redder, whereas the colder parts will be blue. Okay, what have we got after infrared? We've got visible light. So visible light is essentially why we can see everything right now. It's waves that are bouncing off and then going into our eyes, which is why we can see. Let me make this a bit smaller so I can fit more on. So essentially, everything that's before this visible light is safe in a sense. It's okay to be around. Everything after visible light is dangerous. So after visible light, we've got ultraviolet. Now, ultraviolet rays come from the sun or like sunbeds and so on. So these can cause cancer because the sun can penetrate our skin, the UV rays get in, they alter the skin cells, mutate it essentially, which leads to skin cancers. So ultraviolet, quite dangerous. After that, we've got X-rays. X-rays also are quite dangerous from radiation as well. That's the reason why whenever you get X-ray done, you might have had one done at the dentist leaves the room because they're exposed to it quite a lot. So if you're exposed to it once in a while, like when you've broken your leg or you need to check your mouth, it's only once in a while, so it's less harmful. But compared to something that's working there all the time and exposed to it quite often, it's a lot more dangerous for them, which is why they leave the room. And then finally, we've got gamma rays. So the most dangerous out of them all. Okay, so we need to know the uses of each of these, why they're dangerous, and so on. So these will be considered safe right here, and these ones are considered the dangerous ones. So we need to remember that order as well. Now, in terms of wavelength and frequency, well, what is wavelength and frequency? So wavelength is represented by lambda, so just a Greek letter. And again, going back to the equation sheet, it should be there. Let's see. Here you go. So wave speed equals frequency. I'll just write here. Wave speed equals frequency times wavelength, so lambda. So if I wanted to get lambda by itself, I just need to divide by frequency. So wave speed, v divided by f. So the speed divided by the frequency. So the wavelength is essentially one full wave. So rather than me drawing it, I'll just get a picture. Yep, so grab this. So remember we said these are all transverse waves, these electromagnetic waves, not longitudinal. Keep that in mind as well. Okay, so looking at this diagram here, we can see the wavelength is one full wave. So let's make that a bit thinner. So starting from the peak up until the next peak. So it's one full wave, essentially. That's the wavelength. And then the frequency is how many waves are there per second. So something with a high frequency, like this, is going to look something like this, where you've got a lot of waves per second. So high frequency is something like this. So there's loads of waves per second. Let's just say that's 1 second. Whereas a low frequency is less waves per second. Or something like that. So that's a low frequency. So you need to know the what happens with frequency and wavelength on this electromagnetic spectrum diagram. And it's the opposite of each other. I'll do this in red. So the high frequency ones are the gamma rays, X-rays, ultraviolet, and so on. So they're high frequency, more waves per second. That's why they're a lot more dangerous and penetrating. So on this side, we've got the lower frequency ones. And then in terms of wavelength, it's just the opposite. So on this side, we've got the longer wavelengths, which makes sense, right? Because we've got, it looks like this, so low frequency compared to, you can see that's a lot shorter, right? So the longer wavelengths on the left-hand side and the shorter ones are over here. So I'll find an electromagnetic spectrum diagram showing you the waves, so you can see. Yep, so as you can see here, this is pretty good because it also tells you some uses as well. Put this here. Okay, so looking at this, you can see the gamma rays, the waves are a lot closer together to each other. So we can see it's exhibiting that high frequency behavior as well as short wavelength because it's a much shorter wavelength. Remember, wavelength is one complete wave. It's a lot shorter compared to something that's up here, a lot longer. And you can see some uses of it. So X-rays, gamma rays. Gamma rays is a bit of a weird one. So as much as it's dangerous, so it causes cancer. We also use gamma rays to cure cancer, as well by killing cancer cells. And the reason why like you lose hair during cancer using these gamma rays is because you can't target just the cancer cells. Sometimes you target normal human cells as well, like the cells for hair growth, for example. We also use gamma rays as well to sterilize medical equipment when using it for surgery. So as dangerous as these ultraviolet X-rays and gamma rays are, they also have its uses as well. Okay, so that's electromagnetic waves in terms of frequency and wave speed as well. I'm going to wrap it up there rather than starting on something new. But I hope that was useful, and I hope you did understand like how much physics is easy in a sense because you're given all the equations, which essentially is giving you all the answers within physics as well. So I'd recommend when you're revising physics, alone to always refer back to the sheet because you're going to be given the sheet in the exam. So get the one for your exam board. This is what you're going to be given. So always refer back to that as well as revising. So I'll get these sent out. The recording will also go up as well. And I'll also send out yesterday's chemistry one as well right now as well. So I hope that was useful. All the sessions over the last few weeks during December. And hopefully see you in some future ones as well. Okay, thank you for joining, guys.